Welcome to a lesson with Dr. Powell. Let's continue our discussion about derivatives of functions. So here's an example. Suppose we have this function right here, and we want to take its first derivative. Notice we have three inputs, and we have one output. So its derivative should be a linear transformation from R3 to R. So with the column interpretation, it looks like a matrix like this. The different entries where we're sending E1, E2, and E3 are simply the partial derivatives with respect to X, with respect to Y, with respect to Z. So here we pretend like X is the only variable, everything else is constant. Notice what we get, 2X times a constant Y plus the constant Z. Over here for Fy, we pretend like everything else is constant, so we just have, except for Y, so it's constant multiplier X squared is the derivative here. Constant multiplier of Z is the derivative over here. So we get df as follows. So we can, again, use this as a linear transformation, multiplying the input run over here to get an approximate rise. Okay, so wait a minute. We could actually take a second derivative of this. So here's a first derivative. What does it mean to take a second derivative? It means to do the same basic thing. What we're doing is we're looking at what the rise of the derivative would be. Remember, realize what the derivative is. It's a matrix. So, okay, with three different, entries in here. Now, the rise would be another matrix of the exact same size that you add on to it. So maybe this is at a particular point for particular x, y, z values. So this is actually, the derivative is actually a function with three outputs and three inputs. And the rise is going to be a matrix that you can add on to this guy right here as it increases. So as like x, y, z go from one point to another for a particular input, the derivative as a function will have a rise. And so when we think about the second derivative, we're thinking about a way to approximate those rises of this function. Okay, so then again, it's the same basic type of idea. We see where E1 will go, where E2 will go, where E3 will go. E1 represents, so change of X being 1 and everything else 0, so everything else is like a constant. So that's like saying each entry itself, how much it will change um, with respect. So with change of x is 1, assuming linearity, um, assuming that we're actually on a tangent line itself, and so that change of whatever the entry is over change of x is actually equal to the entry, the derivative of the entry with respect to x. So we're actually looking at the partials of each entry here. So you could even think of it the same way as we had before. We take whatever our df was, we take our partial of it with respect to x, partial with respect to y, partial with respect to z. Notice how that looks the exact same as what we did here. We're just replacing the f with df, but it's the same setup. But we're going to write df as a column now, so we would get a matrix. So we write this as a column, and we take the partial of each of these parts with respect to x, the derivative with respect to x. So like right here, so the constant multiply of x is 2y, z is like a constant, so the derivative is just 2y. Here, derivative is 2x, here, derivative is 1. Here, let's see, constant multiplier of y is 2x, z is like a constant, so we just get 2x. Here, that's a constant, derivative 0. That's a constant, derivative 0, because the y is the variable right here. For z, similarly, we get this. So this matrix right here is actually the second derivative. Notice that the second derivative has an input of R3 and an output of R3 as expected, because we're inputting x, y, z, but we're outputting a vector that has the same shape as this matrix right here, which could be thought of as a vector, are the same shape as, the derivative right here, which can be thought of as a vector just on its side as a row, but you can switch it between row and column, if you will. So you can think of it as a vector. So if we go to the second derivative, it's kind of nice because we can think about input a vector and then output a vector as well. So the rise of df we can be approximated in this particular way. So in the next video, we'll expand on this idea and keep going so we can see how we can actually use a second derivative test um, to test if something's a minimum or a maximum by looking at this second derivative matrix, which isn't too challenging to compute if we just think about partials. Like we take the first derivative, we line it up in 3 places, then we just take partials x, partials y, partials z. We end up getting this matrix. And then what we do at our test point, we want to see if it's a minimum or maximum. We put in x, y, and z into this matrix, and then we have some things that we can do on this particular matrix to see if it's a minimum or a maximum. And it just simply has to do with seeing if all the eigenvalues are positive or all the eigenvalues are negative, and that, or if sum of each would mean that it's neither a maximum or a minimum. Thanks for watching.